no resistance
Yeah.
is
Yeah.
voltage divided by
Yeah. So then it was just a little bit shit. It made me really sad going there every day.
how long was the class?
I think it was like 7 minutes.
So,
It was like 2 something.
wait.
Oh, sweet. I think
Oh.
Cool.
There's a
So,
beautiful function called match 9 on a TIA network.
oh, well that will work fine too. But the idea is, I know problem 4 you get this ugly nasty integral that there's no nice closed form solution for. It's going to involve square root, squared trigonometric terms, I think. And the idea there is write out the integral and say, all right, the integral was evaluated using your choice of software to get the final solution in numbers. For those of you that weren't in here a few minutes ago, we were discussing problem 3. I recognize ended up in kind of pain for a couple of reasons. I know from talking to Liam, it wasn't entirely clear what the orientation of the ballast tank in problem 3 should be, whether it's actually a half cylinder oriented with the lengthwise axis pointed upward, or whether it's a half cylinder on its side. So the idea here is you can solve it for a half cylindrical ballast tank in either orientation, and that'll be okay. But more importantly, you probably care more about is that this problem is going to be dropped from the required of the homework and will be made extra credit. Are there any other questions that have been cropping up on the homework that's due Friday? Okay, so we almost made it through, learning why things float, which is a good thing, on Monday. We went through the process of, for the case of a circular cylinder, showing that the buoyancy force is, as Archimedes postulated, equal to the weight of the displaced water, that is rho g times the displacement volume. What Archimedes didn't get to, and what's probably more important to guys that design ships, is where that buoyancy acts. It's, by definition, the buoyancy has to act at the center of gravity of the displaced fluid. Now this is different than saying it acts at the center of gravity of the item that displaces the fluid, right? The idea being, if you have something, if you have a fairly, homogeneous piece of material, let's say it's a piece of plastic, and you throw that into a pool, its density is going to be constant everywhere, whatever is displacing the water, and as a result, if it becomes fully submerged, then its own geometric centroid and the centroid of the volume of the water it's displacing will be concurrent, they'll be at the same location. Which is why if you take something that doesn't have any particular distribution of mass, then it doesn't care what its orientation underwater is, right? If it's something that's floating on the surface, or if, for example, you attached a weight to the bottom of this, then all of a sudden you're moving the center of gravity relative to the center of the displaced fluid, and as a result, the center of buoyancy and the center of gravity are no longer at the same location. And so this gives rise to our notion of stability. And you've probably seen similar demonstrations in early naval art classes, but here's an example of a barge where the center of gravity is fairly low, and as a result, it behaves as any good barge should and doesn't flip over. But as the center of gravity goes higher and higher, it starts to have a more tenuous stability state, and finally, as the center of gravity is raised too high, it just turtles, and you're the naval architect looking for a job. So the definition of stability is, for now, there are tons of definitions of stability. There's many as there are people talking about stability. We call it bounded input, bounded output. The idea here is if you take any system any thing that you want to assess the stability of, and you poke it a little bit, then it should only respond a little bit. So the common analogy is to draw a marble on a track, and the case shown here, if the track has a positive curvature, then perturbing this marble a little bit will cause it to roll back and forth and eventually settle back at the bottom of the circle there. And so you could describe its condition right here as stable. On the other hand, and they're not drawn here, if you were to take that marble and you were to put it on a flat surface, then if you perturb the marble slightly, it's going to move slightly and then stop moving. It won't return to its original state. So this is a neutrally stable situation. And this could be thought of as something like any body that, like as I said, with a constant density that's submerged underwater. You can flip it this way or that, and it's not going to automatically try to right itself. Then the unstable situation is one where if you perturb the marble from its initial condition, at the top of this negatively curved arch, then it's going to dive off the edge. If you're talking about surface ships, usually what you're going to have for a unstable situation is something like this. You're going to have a marble at the top of a hill. This is upright. And my pen works in one direction only. So, this is right side up. If you perturb the marble, it's going to come over here, skitter down to the next stable condition. This could, if for example, if you have a only slightly poorly designed vessel, might be a static lull angle, a few degrees, where it sort of settles into a new stable condition, and you have one of those ships that never wants to stay completely upright. However, in cases like this, shown in the video, this can be completely upside down. So it's your job to design ships that do this. For submerged bodies, the idea of stability is pretty simple. It's very simple, actually. So if you consider something that's completely under the free surface, its entire volume is displaced volume, then it just becomes a matter of the relationship between the center of gravity and the center of buoyancy. We're calling the center of buoyancy just small c, center of gravity is big CG. The idea here being that, for example, if you took I said my ball of plastic that I was talking about earlier, and you attached a weight to the bottom, now the center of gravity is located below its geometric center, right? And so if it's at a stable condition and you perturb it, what you end up with is center of gravity acts through the same position, center of buoyancy acts through the same position because the centroid of its volume doesn't change. It's not dependent on its orientation, it just follows the body's orientation, and buoyancy always acts upward. Same with center of gravity, you're not changing the mass distribution whatsoever. And so what you end up with is now a positive restoring moment, or a couple, where you've got buoyancy pulling up, weight pulling down, and they act to correct it back to its initial condition of roll. On the other hand, if you flip this thing upside down, such that the center of gravity is now above the center of buoyancy, and you perturb it away from its condition, then instead of the center of gravity and center of buoyancy acting to correct the roll angle that you've imparted to it, it's going to act to accelerate that perturbation away from 0 degrees. And so you're going to end up with an overturning moment that's going to try to take it back to its next stable condition, which is this one. So it's going to be an example of when the egg-shaped thing with a mass at the top is perturbed away, it's going to continue rolling because you're simply destabilizing it. In this condition, in a perfect world, it won't move because there's no moment induced on it. The center of gravity, center of buoyancy are concurrent in the vertical direction, so weight and buoyancy simply act to cancel each other and create no torque. But as soon as it's at anything except 0 degrees, no dice. This is a lot more challenging with surface craft, and I am fairly certain if you guys know at least the formulaic way to calculate the metacentric height, right? Have you seen Ixx over volume? Did you go into why that is? Really, did you do the derivation from hydrostatics perspective, or
You might have.
might have? Okay. Candid answer. That's good. Well, it boils down to, we're not going to get into the details of it because it's actually, it's something that's hard to learn and easily forgotten. But if you've got, you know, a surface ship, and you've got one water plane here, one water plane here, and another water plane there, right? So this would be an example of the ship being inclined at even keel and then being inclined at 3 angles. We'll call this A, B, C. So the roll angle at A is 0, at C it's the greatest. Then what you're going to get is, let's say its center of gravity is located here. So you have the weight of the vessel, the displacement of the vessel. At 0 roll angle, its center buoyancy is going to be located at the volumetric center of the submerged portion, so it's going to be about here. We'll call this CB sub A. At the first roll angle here, B, you've now shifted volume away from this part. You've removed this wedge of volume and added this wedge of volume. And so the effect is going to be that now your volumetric center of the submerged portion is going to move over here somewhat. So you're going to have C, B sub B. And then again, as you roll to angle C, and you're removing more volume from here, adding more volume here, it's going to move a little bit more. So C, B, C. And the idea is that for relatively small roll angles, this doesn't hold as soon as you start actually rolling to angles this large, these are going to trace approximately a circular arc about the point that we call the metacenter, or the transverse metacenter. Right? So if you can think about it, it's a case where the metacenter is the point where the buoyancy will always act through for smaller roll angles. And so the point here is that if that buoyancy always acts through the metacenter, then you can essentially, at whatever roll angle the ship is experiencing, or whatever keel angle, you can move the buoyancy force to the metacenter without changing the torque on the vessel, or the moment on the vessel. And what that means is, as long as your metacenter is above your center of gravity, then you, in essence, have a case like this, where it's going to act to restore a non-zero heel angle. So that's as in-depth as we're going to get with the stability of surface vessels shown here. You're going to get into this more when you take NA 321. I think that's with Prof. Bernoulli. And then you've taken NA 270, was that last year, with Mackey?
Professor Back.
Okay. So, and that's so, I guess I'll say one more thing about this. The idea is that because the metacenter depends on how far this sort of swings with small changes in the heel angle, how far your center of buoyancy swings, it's highly dependent on how much volume you lose and gain on each side relative to how much volume stays immersed. Which is why if you have a body that's shaped like this, something that's relatively shallow and wide, compared to a really deep spar, for example, then sallying this thing over at an angle like this is going to cause the center of buoyancy to, the addition of this volume and removal of this volume doesn't move the center of buoyancy very much. So, in other words, you're going to end up with a pretty small metacentric height. Your metacenter is going to be somewhere around there. And so unless your center of gravity is below this point, it's going to be unstable. So shallowly submerged, beamy vessels are more stable because the center of buoyancy tends to swing out further with small changes in the heel angle. And that is as far as I'm going to go into surface vessels. If you do the reading, you will notice that the authors of the textbook do, and here's an example of that spar that I showed where it's not very center of buoyancy didn't move far enough out this way to counteract the weight through the center of gravity. So if you did the reading, you will notice that the author gave a shout out to us naval architects when he said, stability of surface vessels is much more complicated. We're not going to do it, but it's important for naval architects. I'm like, yeah, we're too complicated for you. So today, the rest of today's topics, I just wanted to wrap that up from the last lecture. The rest of today's topics are going to be review of flow descriptions, streamline kinematics, Newton's second law, and streamlines, and this will all culminate in the famous Bernoulli equation. So this is sort of a landmark topic, because as soon as you learn what the Bernoulli equation is, you're going to start using it incorrectly. This is sort of a truism. It's known as the most used and most abused equation of fluid dynamics. That's because everybody, and I mean everybody, at some point forgets some of the assumptions and tenets under which we derive the Bernoulli equation and starts applying it to problems that it doesn't work on. I'm guilty, guarantee you, and Prof. Beck is guilty, and I'm going to do my best to hammer in what those assumptions are so that, maybe you'll be the first in history not to. So up to now, we have not actually had a very dynamic sense of what hydrodynamics is. It's been entirely, everything's been more or less from a static perspective. Did I? Yeah, I entirely forgot my lecture notes. Awesome, we're winging it. So it's been an entirely static analysis. We dealt with fluid characteristics, things like density, specific gravity, viscosity, woo, super fun. Surface tension, hydrostatic pressure forces, buoyancy. These aren't things that really describe how bodies move in water, how they move the water itself. It's more about solving sum of the forces equals 0. Today we're going to actually put something on the other side of that sum of the forces. So we're getting into the real dynamics. As I said, I already kind of went over this. But I'm really going to try to hammer in the assumptions and restrictions on the Bernoulli equation. So this is Daniel Bernoulli. He's a Swiss dude. He had a lot of brothers, and they all seem to come up with really famous mathematical identities. There are some partial differential equations named after another Bernoulli. I don't know, I think there were like 6 or 7 of them. It's kind of obscene. Alright. We talked about the difference between Lagrangian and Eulerian particle descriptions on the first day, right? Lagrangian is following a specific particle. You tag somebody with a GoPro and you watch the video as they walk through Manhattan, right? So this is usually what we use when we describe rigid body mechanics. If you say you throw a baseball, somebody says compute the trajectory of the baseball or how far it went given an initial trajectory. Then you're using the Lagrangian approach, where you say I'm going to follow this particle or this object. I'm going to see what forces act on it, and I'm going to compute its resulting motion. So this is where we apply Newton's second law to individual masses or particles and trace them through time. Eulerian descriptions, on the other hand, are these sort of big picture field observations where we say at a given point we're only going to look at this one point, but we're going to see every single particle that passes through that point. So instead of saying, here's a particle and it's going this direction, and then sometime later it's going this direction, and sometime later it's going this direction, this would be Lagrangian description of this particle where we have time. What you'd have instead for a Eulerian description, you say I'm going to pick, you know, this point in space, and then every particle that passes through it as time advances is going to be going, you know, in this direction, so that there ends up being a path of particles going from this point in this direction. So in my analogy with GoPros, this was sticking a GoPro on a walk signal and sort of seeing how many people per minute cross the crosswalk, as opposed to assigning somebody to count and keep track of every person in Manhattan and just seeing how many happen to be crossing the crosswalk at that given time. Review, we've got streamlines, streaklines, and pathlines. So recall that streamlines are a very Eulerian concept. This means if we know the velocity everywhere, we have our Cartesian grid, x, y, and we just happen to know that the velocity at these points goes in these directions. That is, fluid particle passing through these points will always be directed along one of these. Then the resulting streamline is just a matter of playing connect the dots. Right? It's tangent to the velocity everywhere in the field, which means you have to know the velocity everywhere in the field to get a bunch of streamlines. Streaklines, on the other hand, are the instantaneous locus, or all the points connected together that once passed through a given point in this Cartesian grid. So if the flow isn't steady here, for example, if the velocities are changing and waving all around with time, then you may have that the particles that pass through here, one ends up over here, one ends up over here, one ends up over here, one here, here. And so these are kind of, if you trace back, these are all the particles that passed through this original x naught. And so the, let me find a different color, the resulting streakline would look like this. Path lines, on the other hand, are the trajectory of a given particle. Sort of like a long exposure photograph, you see everywhere that single particle has been. So this is sort of a Lagrangian concept where you have to follow that one particle. So if this flow is unsteady and this particle got here through time, it could trace an entirely different path. It may have, you know, gotten here by traveling along this path. So the nice thing to remember here is that when the flow is steady, these are all the same. So this is a tool we use a lot. It's certainly one we're going to use today. So before we really get into this, the Bernoulli equation in the form we're using today, there are other forms, requires flow that is steady, that occurs along a streamline, and flow that has shear stresses neglected. Again, we're assuming no viscosity, basically. That is, fluid particles are only acted on by surface forces due to pressure, and body forces due to gravity or some other conservative body force. So when I say steady flow, I just want to be clear here. It's termed steady if the derivative of a given variable with respect to time is equivalently zero. For example, the velocity measured at a point. I gave you an example if you're measuring the velocity at x naught here. If what you get is, say, your u and v velocities, or the magnitude of the velocity, all components stay steady with time, it's steady. However, if they're going all over the place, that means this velocity vector is, you know, waving across the clock face. Then now what you've got is u as a function of time that is changing. So this is an unsteady flow. Now this is a kind of neat demonstration, but remember I mentioned that streamlines or streaklines are path lines in steady flow. And this is what that actually looks like. So this plane, yeah. So these are little pulses sent along a smoke trace flowing around a body. And what you see is that these can be thought of as little particle packets, right? These little wide spots in the smoke trail. And they tend to kind of ride along these lines as if they're rails. So these are actually the streamlines in this case. and the streaklines equivalently. And then because we're seeing that each packet of particles follows the same one, then we can see that they're also path lines. I want to point out that over here we see what's called a stagnation point. Let me play that one more time. Yeah. So a stagnation point is defined as a location where the velocity goes to 0. So for this streamline right here, particles that are traveling right along the center of this sort of hit this point, and they won't be able to go either direction, which is why you end up with this sort of accumulation of particles. And so the velocity goes from whatever it is up here to 0 and stagnates. So that's going to be an important concept when we get into calculating it's called stagnation pressure with the Bernoulli equation. There we go. So if we refer to the streamline as, I guess technically these are path lines because these are convected dye streams. But for steady flow, as I said, they are also streamlines. And if we take one of these streamlines and throw a coordinate system onto it, we're going to have, well, first we're going to have our global fixed coordinate system, or XYZ description, right? But the streamline doesn't necessarily have to have any particular orientation with respect to our Earth fixed coordinate system. So it's much more convenient to assign a new coordinate system that we're going to call the normal and streamwise coordinates. So the streamwise coordinate is just the unit vector that's tangent to the direction of the streamline at that point. Normal is just normal to the streamline along the direction of positive curvature. Okay. So let me see. One moment, guys. Okay. So this is how we're going to go ahead and start talking about motion of particles along these streamlines. We saw in that last video that fluid particles entering over here tend to ride the streamline like it's a rail. And so a couple of quick things. We tend to describe the streamline, or describe forces and such on the streamline in these streamwise fixed coordinates. But how do we actually describe motion along the streamline itself? And so this is when we start to talk about streamline kinematics. So because the particles are always following along the streamline, we tend to measure their traveling distance as the distance along the streamline, s. This isn't s hat, this isn't a vector quantity, we'll just call this s, as a function of t. That is the distance measured from, say, point 0 to point 1. This would be the entire length of this curve, not the x direction, not the y direction, but the integrated length traveled along this curve. So we have the distance along the streamline, and then we also, the second descriptor of the shape of the streamline that we have is, if we have the distance, we also have the, how do I want to write this? The radius of curvature as a function of s. That is the instantaneous amount of curvature present in the streamline. And so this is a function of the length along the streamline. And with these two quantities here, the distance along the streamline and the radius of curvature as a function of the distance along the streamline, we can completely describe the shape of the streamline itself. So I mentioned that s and n are the two tangent normal unit vectors. Okay. So s hat, unit vector along streamline. Anybody see a way that we can actually represent s hat as a function of the velocity? Right? If the point on the streamline if the velocity on a streamline is by definition tangent to the streamline there, that's what makes it a streamline, then s itself has to be also concurrent with the direction of the velocity, right? And since it's a unit vector, we can actually define s as the velocity at a point divided by its own magnitude. Okay. Good. Now the question is, how do we define the actual velocity, right? Look, for now, we're going to go ahead and, just for the sake of convenience, we're going to drop the vector notation and simply say that v, if I draw it without an arrow, is equal to the magnitude of the, so just v is the scalar magnitude of the velocity. Well, because the velocity, it's everywhere tangent to the streamline, that means it only travels along the streamline, then if v is the amount of distance traveled per unit time, and s is the amount of distance traveled as a function of time, then we can actually define v as ds dt, right? Does this make sense? This is it's changing direction, so it's always orienting along the tangential unit vector, but its magnitude is given simply by the rate of change of the distance along the streamline with time. So so this ends up becoming a, well, yeah, we'll get to that in a moment. So the next question is, how do we describe accelerations? You know, I said kinematics, we've got position, we've got velocity. The other major quantity that we worry about in kinematics is acceleration. So because acceleration is a vector quantity and we're going to want to be concerned about this vector quantity, let's first focus on acceleration in the s direction, right? Velocity is always in the s direction. That's been established. There's no component of the velocity that's normal to the streamline, otherwise it wouldn't be a streamline. So we're going to have acceleration is equal to this as times s hat plus an times n hat. And we want to look at this as term. So as, acceleration is equal to what? Time derivative of velocity, right? Our velocity here is given as a rate of change of s with a t. So anyone want to, you know, hazard a guess at how we compute the streamwise acceleration? Think chain rule. You know, if we have the velocity is a function of s. It changes along the streamline, right? How would we write dv dt? Well, when you have a function of a variable that's not the one you're taking the derivative of, right, you end up with dv dt is equal to dv ds times what? ds dt, right? ds dt. And we showed right up here that the velocity is equal to ds dt. So this term actually becomes velocity. And so our acceleration along the streamline can be expressed as v times dv ds. But, wait, hold the phone. Didn't we just say we were talking about steady flows? Right? No changes in time, so what business does acceleration have being in this problem? Well, this acceleration occurs not because a given point in time, or a given point in space is changing in time. It's because the different velocities are occurring at different points in space. As an example of when this might happen, let's go ahead and let's imagine we have a nozzle, right? Flow coming in this direction. So we've got streamlines. Going from the wide end of the nozzle to the narrow end of the nozzle. So if I take a point here, point 1, and I take a point here, point 2, just by intuition, what would you have to say about the velocity at point 2 relative to the velocity at point 1? It's going to be greater, right? So that means V1 increases, or sorry, V increases from point 1 to point 2. At the same time, does this necessarily have to be unsteady? Does this have to be changing in time, the way that the fluid is flowing through this nozzle? Turn on a garden hose. It can be steady state, but if you put a nozzle on that garden hose, you're still going to get an acceleration of the flow from here to here. And the reason is, the velocity at point 1 is going to be constant in time. The velocity at point 2 is going to be constant in time. But a particle, as it moves from point 1 to point 2, is going to be convected through a bunch of different points, which each have steady velocities in time. And so the idea here is that we have dv ds, that is the rate of change of the velocity along the length of the streamline, not with time. But because v is convecting that particle along that streamline, it's going to start seeing an acceleration induced by the changing velocities in space. And so this convection effect leads to what we call convective acceleration. And this term is going to come up when we get into, I think it's the next chapter, Reynolds transport theorem, where you end up with a term called exactly that, the convective acceleration. So that's how you get acceleration in a steady state flow. Does that make sense? Anybody murky on that? Okay. So what about acceleration normal to the streamline? I know we're not gonna use it yet, but I'd like to go ahead and cover it just for the sake of completeness. Acceleration normal to the streamline. This one's a little tougher, but anybody have a notion of how, if we're describing this by radius of curvature, that means we're approximating a point here as curving as if it's a circular arc, right? And the acceleration normal to a circular arc should be something that you've covered in basic physics, like swinging a ball around your head, or the car rounding a hairpin turn, right? It's this thing called radial acceleration. And how would you write that? What's the generic equation for radial acceleration directed towards the center of a circular arc?
Is it velocity over radius of curvature?
That's close. V squared over R, right? So V squared over the radius of curvature. And that's as simple as that's it for your normal acceleration, right? So we're going to go ahead and summarize these two normal S is equal to V dV ds. So these are our two accelerations. They make no assumptions about the orientation of S and N, or the relationship to our Earth fixed coordinate systems, X, Y, Z. They can pretty much be pointed any dang direction they like. So what we're going to be doing in the next couple slides, or the next couple minutes on the board, is actually using good old Newton's second, F equals ma, applied to this particle on a streamline, right? The idea is we're going to, instead of putting our vectors in x, y, z components, I, j, k, we're going to put them in streamwise and normal components. And since we have expressions here for the accelerations, we can plug these in through our A vector. And so it's our job to come up with what force components drive the motion of a little particle mass that's attached to a streamline. So, okay. So, right now, remember I said we're assuming there are three key assumptions. One was that this equation applies only along, or analysis applies only along a streamline. Steady flow, and the third was that we're assuming inviscid flow, that is, the viscosity is zero. As I mentioned before, this is a completely incorrect assumption. There are no such things as inviscid fluids, but there are some really nearly inviscid fluids. Viscosity of water is not all that high. So for a lot of flows, especially things that aren't located right next to a wall where your boundary layers, inviscid assumptions work really well. Pretty frequently, guys, in aerospace groups, drop viscosity altogether because they're really high around those numbers, and the flow is even less viscous than water. So this is a good idealization for cases where the viscous forces are much weaker than the other forces present on the fluid, this being body and surface forces due to pressure gradients. As I mentioned, boundary layers are one example where this entire analysis and thus Bernoulli's equation are a big no-no. Alright, so we need to take a closer look here. Said if we're dropping viscosity, and there are hints right up there, then what are the two sort of sources of force that we need to worry about on a given fluid particle? Alright, I'm going to go ahead and start drawing a fluid particle. Well, anybody want to let me know what the two types of forces are we'd expect to see? We're leaving viscosity out of it. Pressure, good. And gravity, good. Body forces, pressure-induced surface forces. So we're going to check these off as we account for them. Pressure and weight, right? So let's assume this is a small, this blue line here is a streamline. So the velocity everywhere here is tangent to the streamline. And then we've got this small little fluid volume with length ds, height dn, and then we'll say that it has a depth of dy. Right? So now let's go ahead and set up our streamline fixed coordinate system. So this one here is our normal unit vector, and this is our tangent unit vector. Note that this constitutes a rotation through an angle of theta relative to our Earth fixed coordinate system, right? So relative to the horizontal plane, this is some angle theta, which means that our first force here, weight, let's go ahead and cross this out and draw this in as weight, right? Let me reorient that so it's directly downward. So we've got weight, which now is acting in some component along the normal direction and some component along this streamwise direction, because it's not oriented in any one axis entirely. So we're going to say weight is equal to Ws times S plus Wn times the normal unit vector, right? And the way we're going to compute that is, of course, using a triangle identity, saying this is weight, this is theta, this is going to be weight n, this is going to be weight s. So let's pick a direction to concern ourselves with first. actually in the next lecture we're going to be doing motion normal with the streamline. So right now, let's constrain ourselves to only the forces that are occurring along the streamline itself. So what component of weight's going to be directed along the streamline? Alright, we know the weight is the hypotenuse of this triangle at angle theta. What's this component that's directed along the streamline? Just this leg. Okay. It's just W sine theta, right? So our, let me find somewhere to put our sum of the forces. So there's weight. Let me move our sum of the forces up here. Sum of the forces in the S direction equal to, is that going to be positive or negative? The weight. Negative, yep. It's acting this direction to sort of push the fluid particle back downhill. So we've got W sine theta now plus our pressure forces, right? So let's assume we know the pressure at this point. This is going to be some P naught, right? And remember how we did it in hydrostatics where we said, now we know the pressure P naught. This is a very small length, so we're going to use what to estimate the pressure at nearby places? What type of expansion, estimation? Some might call it a series. Taylor series, yeah. All right. So pressure at this location, right? The streamlines location of this is going to be, well, let me draw it in red. So we're going to have pressure forces acting here. We're going to have pressure forces acting here. Pressure downstream by a first order Taylor series expansion. Anyone want to volunteer that expression? We know P naught. We know that the distance from here to here is ds over 2, right? And first order Taylor series expansion means we're assuming we only keep the first derivative of P with respect to S. So dP ds. How do we combine those terms to estimate the pressure at this location? Anyone got a guess? It doesn't have to be a right one. That's okay. I did this in the hydrostatics. This was one of the big ways that we derived that delta operator, right? Or the grad operator, the gradient. It's also in homework 1 doing first order Taylor series. Remember, f of x that is close to some x naught is equal to x naught plus df dx times x minus x naught. The point, the slope, and the distance from that point should give you the new elevation, right? So how do we apply that to find the pressure here if we know P naught?
Would be P naught, excuse me, plus ds dt times ds over 2.
So P naught,
Or
not ds dt, but you're on you've got the right form there. I mean we're trying to evaluate what pressure, right?
sure.
And so we want the linear approximation to the rate of change of pressure along S, right? And so it's dP ds. Yeah. P naught However, are we going upstream or downstream from this point, along the S or along negative S? Negative S. So we're going to go and say P naught minus, well, we can do plus dP ds, but then the distance that's traveled from this point is going to be negative ds over 2, right? So over here, we've got P naught minus dP ds over 2, and then this whole thing needs to be multiplied by an area, which is going to be delta y by delta n, right? This is times delta y, delta n. So this is the pressure force acting on this face of our little fluid volume. All right, this face. Someone should have an easy time now with the pressure Taylor series on this face.
Plus instead of minus.
Exactly. Yep. P naught plus dP ds dy dn. Sorry, that is not what I meant to do, times ds over 2 all times dy dn. All right. And that's it. We have our pressure surface forces and we have our weight. So let's go ahead and plus P naught minus dP ds over 2 dy dn minus P naught plus P ds d delta s over 2 all times dy dn. Okay, now let's start populating some of these terms and doing some simplification. The weight is simply equal to what in this case? We've got ds, dn, dy, it's a fluid. It's going to be rho volume. Alright, so what should we plug in for W?
ds, dy, dn times rho.
Good. Yep. So I'm gonna go ahead. And we're gonna want that back later, so I'm gonna. Okay, so some of the forces, S is equal to, forgot the minus there, minus dy ds dn times rho times sine theta plus, we can see right up front here there's some cancellations we can do, right? We've got P naught minus P naught. And we've got a minus dP ds ds over 2 plus another minus dP ds times ds over 2. So grouping these together, we should simply get dP ds times ds dy dn. Yes? Makes sense?
Minus.
Huh?
Minus.
Minus, you're right. Thank you. Minus. All right, now some of the forces is going to be to what? By Newton, MA, right? And M is, we forgot a G here, that's the weight. equal to MA. Well, since it's all along the streamline, MAS. And M is going to be equal to rho dy, ds, dn, and A is simply equal to, as we wrote it up there right before I erased it, V dv ds. Yeah? So, plugging all of these in, we're going to get equal to negative dy, ds, dn, rho g sine theta minus dp, ds, ds, dy, n. We've got this little volume term, right? This dy, ds, dn in all of our terms in the equation, so we can go ahead and cancel that out, leaving us with rho v dv ds is equal to negative rho g sine theta minus dp ds. Sine theta. If we look at this really carefully, let's zoom in on this little portion of the body right here. I guess I actually want this to be a z and this a y. This doesn't matter much to it. Y, z, s, delta z, delta y. Right? Small element of s, and this is going to be theta. So a small little section of the streamline located at angle theta is going to go through delta y in the horizontal direction, delta z in the vertical direction. So we could say that delta z is equal to what? Delta s sine theta, right? Delta z is equal to delta s sine theta, which means that sine theta is equal to delta z over delta s. And as these lengths get smaller and smaller and smaller, remember we're taking the limit as this entire thing shrinks down to an infinitesimally small point. This ratio, delta z over delta s, will become a proper derivative dz ds. So what this is telling us is that sine theta is equivalent to the rate of change of z with s. Right? So we can go ahead and make that substitution right here. dz ds. Well, awesome. Now we have a bunch of stuff all involving derivatives with respect to s. When we see a bunch of derivatives, we do what with them? Integrate. We love to integrate. But first, let's go ahead and move these negative terms over to this side of the equation. So we end up with rho v dv ds plus rho g dz ds plus dp ds is equal to 0. Additionally, just for giggles, we're going to take this rho and we're going to go ahead and divide it out from both sides of the equation, so we end up with 1 over rho dp ds. Alright, now let's integrate both sides of this with respect to s, which is going to lead us to, well actually I missed one step here. This v dv ds, we want to put this in terms of purely a quantity of s, because v varies as a function of s, right? So we can recast this as 1/2 d ds v squared. Does this little step make sense to everybody? Being if you take the derivative of v squared with respect to s divided by 2, it's simply reversing the chain rule. I just did one step of integration as a substitution. So now, if we make that substitution in for the v dv ds, which remember is our acceleration term, what we've got is now acceleration our weight and pressure force plus equals 0, right? So everyone follows so far how we got to this stage in the equation. Writing it all out, just a matter of canceling out little volume terms and then making substitutions for sign, making this substitution so that V is now, everything in here is a constant multiplied by some derivative with respect to S. So now, if we integrate, I got a little ahead of myself there, which is going to lead us to, in this case, because everything is simply a derivative with respect to S, we're going to end up with V squared over 2 plus GZ plus, this one's a little bit trickier, I'll get to this in a moment, 1 over rho dp ds is equal to, sorry, not 0, the integral, 0, indefinite integral is a constant, right? So why did I leave this one inside the integral? 1 over rho dp ds. Well, we haven't made any assumptions yet. None of the assumptions that were made, that is, streamlines, steady flow, inviscid. Was there anything in there about incompressibility? No. So we can't make any assumptions yet about how rho or pressure vary along the streamline. Examples of how we could assume is we could say it follows the ideal gas law, and here's the pressure along the streamline, for example, so you can calculate how rho varies. But in general, you can't integrate this if you don't know how P as a function of S changes, or how rho as a function of S changes. What we're going to do right now is make the assumption that the fluids we're working with are incompressible. And this is a pretty good assumption for most cases. As a rule of thumb, if the speed of the fluid is less than about 0.4 times the speed of sound in that fluid, then an incompressibility assumption is relatively good. This is a rule of thumb because, for example, if you're driving your car down the road, speed of sound in air is about 760 some miles per hour. So unless you're going 40% of that, or 300 some miles per hour, then you're actually moving the air out of the way more than you're causing it to compress. Right? Its own mass is not so great that it can't get out of the way quickly. In water, because the speed of sound is even higher, I forget what the speed of sound in water is. It's really large. That's why sound travels so well underwater. And incompressibility holds, and even to extremely high speeds until you hit cavitation. So for now, we're going to make the assumption that that rho is a constant value. It doesn't change throughout the fluid, which means that the integral here is simply going to give us P over rho. So now, this may seem redundant, but we'll go ahead and multiply this rho back through one more time now that we've made the assumption. I'm going to write it over. Here we end up with 1/2 rho v squared plus rho gz plus p is equal to 0. And this, ladies and gentlemen, is the Bernoulli equation. Right? This is the much celebrated, much used, much abused, loved, hated, in all forms, Bernoulli equation. This is what allows us to say why planes fly, why propellers work, why rudders work. And essentially, at its core, it is conservation of linear momentum. It's F equals ma applied along a streamline. Simply saying fluid, we already know that these fluid particles in steady flow are following the streamline. So at the point on the streamline, let's figure out what forces are acting on those fluid particles. Let's figure out how much they make those particles accelerate, and let's group all those terms together, and what falls out is this, where we have velocity, we have a gravitational component, it's rho gz, and we have a pressure component. So, let me put that back. Okay. So we already went through all these steps, figured out the free body diagram of the fluid particle. What came out was the Bernoulli equation. And so, remember I said, P plus 1/2 rho v squared plus rho gz is equal to constant. What that means is that along the streamline, if you take 2 points, your point 1 and your point 2, that the Bernoulli equation, that constant, isn't changing. It's constant along the streamline. And so you can say P1 plus 1/2 rho V1 plus rho Z1 is equal to P2 plus 1/2 rho V2. The quantities at point 1 can be used to infer the quantities at point 2. Remember the conditions under which this applies. Points 1 and 2 have to be on the same streamline. The fluid density for this form has to be constant, which means it's incompressible and homogeneous flow. The flow is steady. The velocity is not changing in time. It can be changing along the streamline, but then that change in streamline, or velocity along the streamline cannot itself be changing in time. You can't have an evolving flow field. And the fluid has to be approximately inviscid, because in this free body diagram, we left out all of the frictional components, which would be acting on these faces, right? Shear stresses were left out entirely. Please, please, please commit these conditions to memory whenever you are using the Bernoulli equation. You're going to be using it a lot. And let's see. I wanted to point out that when we wrote out our first form of the equation of motion here, right, our sum of the forces in S is equal to let's see, when we had our rho v dv ds is equal to negative dp ds minus rho g sine theta, right? This is one of our intermediate forms of the equation. You've actually seen this before. We derived this when we were doing hydrostatics, right? In that case, however, we said that this was equal to 0. We said this was the gradient of the pressure. We said this was rho g. So remember that we said, when we said that 0 was equal to negative gradient pressure plus rho g, this was the hydrostatic equation of fluid equilibrium. And all we've done here is we've taken these same pressure gradient and gravitational body forces and projected them along the s-axis. So each of these terms could be thought of as the dot product of the s unit vector with these vector components in the equations of motion. Simply now, all we've done with the left-hand side is instead of saying it's 0, as is saying it's static, we've come up with an expression for the acceleration in that s direction. Okay. So, let's show some examples of how we use the Bernoulli equation and how it gives us some insight into the flow. First, something pretty qualitative, kind of easy if I can get, there we go, blackout. Behold our nozzle from before. Remember, we said that V2 is greater than V1, right? That was the inference. It's going to travel through a smaller area, it has to speed up. I am sorry, I wrote the Bernoulli equation wrong. That's not 0, that's constant. That is, shame on me. Constant, not 0. The integral is equal to 0. Or the derivative is equal to 0. Okay. So let's assume that we're evaluating points 1 and 2. Now let's say that we've got y and z. Well, points 1 and 2 are at the same z location, right? So if we're writing the Bernoulli equation as rho over 2 v1 squared plus rho gz1 plus p1 is equal to rho over 2 v2 squared plus rho gz2 plus p2, right? There you go. We'll put the same constant along that streamline. We can subtract z1 equals z2 from both sides, right? So what does this tell us about the pressures at point 1 and 2? 2 is going to have a smaller pressure, right? Because the relationship here implies that as V goes up, pressure goes down. This is the equation behind, as I said, showing why wings work, right? The flow over the top of the wings faster, pressure decreases according to the Bernoulli equation, creates suction. Sucks planes up into the sky. So now let's look at a. There we go. I'm gonna go ahead and erase this. Anyway, the rest of these slides, the rest of the lecture is simply just going to be applying the Bernoulli equation to some really simple examples. So before we do that, any questions on how we got to the derivation of the Bernoulli equation? Nothing? Straightforward-ish? See a couple of grimaces. Alright, I'll take your word for it. So let's consider a reservoir, a tank of water. That is the velocity everywhere 0, it is quiescent. We've got, I don't know, let's put a point on the free surface and then a point anywhere else in the fluid, we'll say at some depth h, right? So fact 1 is that because the velocity is everywhere, let's go ahead and get rid of those terms. Right? So now we've just got P1 plus rho gz, P2, rho gz. This is starting to look like our fluid statics equation, right? So that means that the pressure at 1 plus, this rho gz1, so means we can move things around and get the pressure at 2 is equal to pressure at 1 plus rho gz1 minus z2, which in essence becomes P2 equals P1 plus rho gh, which is exactly the same thing we got using our good old, 0 equals rho g minus grad p, right? Same equation, because they came from the same equations of motion. In this case, we said nothing's moving, so it sort of forces the Bernoulli equation to satisfy this right here. Note that I said the Bernoulli equation does not, only applies along streamlines, right? This is one case where it's a little bit confusing to say, well, what constitutes a streamline? If nothing is moving, then what is a streamline? In general, for quiescent fluids, ones where nothing is moving, then you could say any points are, in essence, streamline, along a streamline. Right? So you might imagine that under very small inviscid motions, point 1 here might circulate down to the bottom, point 2 might find its way back up. But if the velocity is 0 everywhere, you can apply the Bernoulli equation between any 2 points. Okay. Let's consider the case of a bicyclist. He's riding along with a forward velocity v0. And so let's figure out what the pressure up here versus the pressure on his face are. So the first question is, what do we use for our frame of reference? Right? What coordinate system do we need to use? Remember that we need to treat this as a steady flow assumption. So if we pick, right here as a coordinate system, well, we've got that the flow, or that the air is still, right? He's not riding into a wind, he's just riding in still air. So we could say that the velocity here is 0, but as he rides past, the velocity here is going to get perturbed and go all over the place, and then go back to 0. So that means it's an unsteady coordinate system, right? However, if we put the coordinate system on his nose, and simply say that it's advancing with him at speed v, V naught, then you never that coordinate system doesn't see any unsteadiness. It's simply advancing with the constant inflow. It's always got a stagnation point on its face at the same point in the coordinate frame. So we'll go ahead and put the coordinate system. Oops. Come on. There we go. We'll go ahead and put the coordinate system right here, which means that right on his face, what's the velocity going to be? As I said, we call this a stagnation point, right? So the velocity is going to be 0 over 2 seconds space, which means that in essence, in this coordinate system that is fixed on his nose, what is the apparent inflow velocity? V naught. Yeah. Oh, well, first it's going to ask us, is there any change in elevation from this point to this point? No? Alright, so let's cancel out the z terms. And then the inflow velocity is, as you said, going to be V naught. Alright, so we've canceled out most of the terms in our Bernoulli equation here. So what that leaves us with is P1 plus rho over 2 V1 squared is equal to P2, right? Or P2 minus P1 is simply equal to rho over 2 V1 squared. And V1 squared is simply equal to V naught, right? The speed of advance of the bike, which is exactly what we get here. And so this is what we call stagnation pressure. Notice this falls out from the first term of the Bernoulli equation. Now this is simply the pressure that develops whenever a moving fluid is brought to a stop. Okay, so I remember once I brought up the example of, I think when we were talking about the continuum hypothesis, if you're standing out in a hurricane, what is it that's creating that, what is it you're feeling when the wind's blowing on you? It's actually the Bernoulli equation in action. The wind is stagnating against your body. You're getting this rise of pressure equal to rho over 2 V naught squared. V naught's the wind speed. And so it's creating this big force pressure imbalance on one side of your body, just attempting to blow you backwards. So, okay. If the bicyclist, however, were not moving along at a steady velocity, then our coordinate system would be accelerating in space, right? And our V1 would be changing in time. So we'd have an unsteady situation here, in which case I'm not going to show you mathematically how, but this form of the Bernoulli equation, which is the steady Bernoulli equation, would give you a complete bogus answer. It would be totally wrong. So be sure that whenever you're applying the Bernoulli equation, whatever frame of reference you use, whatever coordinate system you use, it sees everything in a steady manner. So Bernoulli equation is, as I said, it's F equals ma along the streamline. It's also a way of expressing a conservation of energy, where P is your sort of potential energy, your pressure energy, rho v squared is your kinetic energy, and this is your gravitational potential energy, right? The idea is that the conservation of energy says that these have to be constant. All the forces here are conservative. Gravity and pressure don't cause any, heat dissipation, and so we don't lose any energy to thermal losses. So if we divide through by a rho g term, what we end up getting is pressure over gamma plus v over 2g plus z. And so all of these terms actually have units of length or dimensions of length, right? And so what we call these then, this is the, some people call this the head elevation curve, or the head elevation equation. But these different terms then are derived where this P over gamma is the pressure head. This is the height of a column of liquid with specific weight of gamma that would be created by the static pressure at that point, or the actual measurable pressure. The elevation head should be pretty simple, it's simply how high up it is. And the velocity head is if you, went out in your hurricane and you stuck the end of a manometer out into the wind, such that the wind came in and stagnated against the end of the manometer, it would drive the fluid up by this distance, this head. And so the sum of them, this constant, we call the total head. And it is the total head is conserved. And you get into marine engineering classes and such later on, you'll start talking about things like total head loss and minor head loss and major head loss, which occur in pipes, which happen when you start adding in frictional losses into this, and you have to account for the fact that your head, total available head, decreases. All right, so that actually wraps it up. I managed to make it through all of that today. So next lecture, we're going to start talking about how do we apply Bernoulli equations, things like pitot tubes, which are essentially glorified manometers, free jets, open channel flows, and we're going to derive the Bernoulli equation in the direction normal to the streamline. It can allow us to do things like compute the pressure at the center or the eye of a tornado. Don't forget, homework 2 is going to be due on Friday at the beginning of lecture. That problem number 3 is extra credit, so make a, take a gander at it. And homework 3 I'm going to be uploading later today. That will be due next Wednesday.
I was about to ask, can you like make all the homeworks due today? Because then we have like a weekend and then like a full week of tutor before we have to turn in the homework. If that makes sense. So we have like a weekend to look at it and then we have 3 opportunities throughout the week to like try to get it fixed.
I could think about it, but I guess the reason I like Wednesday is because it's sort of you get the homework after you've seen the introduction to the material that's on the homework, and then you finish that material and then the homework is due like 1 lecture later. And so it gives you kind of time to work through it as you want to material. But I wouldn't be opposed to having it do it Friday.
So much work means is I have like, I haven't, because I'm used to like looking at things at like the end of the week, so it's like, oh, it's due Wednesday, and so in my mind I'm not going to look at it until Monday, and then I only have 2 days to work.
Oh, well, that's not my fault.
I know, but it's like a, yeah, but they're out of order.
You just
In a,
read the brain.
what? We do my homework due Friday, because then I have to look at it, and then just.
It's the same amount of time.
No, it's the same amount of time, but it's the shift in. It's more convenient to shift.
Plus,
the
you
time.
already have tutor hours on Monday and Tuesdays.
And Thursday the day after it's assigned.
And then Thursday, the day after it's assigned for those that want to get a jump on it.
3:10 working Mondays.
Your pants are so comfortable. Yeah. Like, I thought you were wearing pajamas for a minute. No.
How does that not
You're
throw
just
you
really.
off?
What?
3:10 working Mondays.
No, it did throw me off.
Obviously. Oh, yeah, because I'm a show. Yeah, you are. Don't make that noise, you're going with me.